Section 5.7, applying the fundamental theorem of algebra. We've worked with factoring, we've worked with grouping, we've looked at zeros, and we're going to emphasize some more work on the zeros specifically related to the graphs. And this fundamental theorem of algebra helps us determine the number of zeros we're going to have, some of them being real, some of them being imaginary. And it states if f of x is a polynomial of degree n, where n is positive, that's all that means, then the equation f of x equals 0 has at least one solution in the set of complex numbers. Given complex numbers, a plus or minus bi. And it might be just the a part, the real part, or it could be the combination and thus be complex. The corollary to the theorem, if f of x is a polynomial of degree where n is positive, then the equation f of x equals 0 has exactly n solutions provided each solution repeated twice is counted as two solutions. If it's repeated 3 times, 3 solutions, and so on and so on. So basically what we're looking for is the degree of the function determines how many solutions we're going to have, and then later throughout the section here we're going to learn how do we know if they're real or if they are imaginary. So that's where we are headed. First 2 examples, pretty straightforward. How many solutions do we have? Making sure that our function is in descending degree order. It's very easy to tell by looking at the lead term, and specifically the lead power, to know the number of solutions we're going to have. So since this is a 4th degree polynomial, we know we will have 4 solutions. They may not all be real. Some may be imaginary. But that's how many we're going to have. And then with b, again, making sure I'm in descending degree order. 3rd degree, telling me I'm going to have 3 solutions. So that's the quick way to determine the number of solutions. And that's what the corollary and the fundamental theorem are getting to. Checking out our degrees of our functions. Now, we're going to go actually find out what they are. How many do we have? And are they real? Are they imaginary? So back to looking at the zeros. Remember that when looking for zeros of a function, it's important to remember that that means the function is set equal to 0. And lead term degree of 3 means that's how many solutions we'll have. Now we're going to go find them. 4 terms, that's the one where we might be able to group. And in this case, if we paired the first 2 together, and we pulled out a GCF of an x squared, we'd have an x plus a 1 left over. And if I paired the second 2 together and pulled out a negative 3, I'd have an x plus a 1 left over as well. So we end up with our common binomial, which means this polynomial can be rewritten as x squared minus 3, this quantity x plus 1 equals 0, and now we just simply have 0 product property to find our zeros. Both of these yield real zeros, so we get 3 zeros, which is the number of solutions we were supposed to have, so all of our solutions just happen to be real in this case. B also 3 solutions, and it looks as though in this case we are also able to group, so that's convenient for us. If we don't group, then we're going to have to set up our rational zeros theorem. So we get an x minus 2, then grouping the last 2, pulling out a negative 9, get an x minus 2 again. And of course, these would all be set equal to 0 because we're finding zeros. And then x squared minus 9, binomial, x minus 2, difference of 2 squares, 3, and 2. Again, 3 solutions, they just all happen to be real. So we've been talking a lot about how these zeros are going to be helpful for us graphing-wise. Before, with the first sections of the chapter, we just simply graphed based off of in behavior and a t-chart or synthetic substitution. Well, the nice thing about finding zeros is that it can be useful for us in the graphing process. So here, this is where we start to transition. We're going to take graphs and interpret the graphs that come up with our functions. And we're going to interpret them in a factored function way so that we can use the zeros. So over to the right, we've got that graph crossing it, or not crossing, but hitting the x-axis at -1. And we're crossing at 2. So this is a unique x-intercept here, this -1 value. Notice the graph comes from below, it hits the x-intercept, and then it continues back down. Now this is an example of the 2 scenarios we can have, graphically speaking, at our zeros. So now we're talking about behavior near the zeros, where before we were focusing on the in behavior. The graph is going to do one of 2 things at your zeros. The graph will either bounce off of the zero, or the graph will go through your zero. And how do we know which is which? When the graph bounces off, as in the case of -1 here, what's happening is the graph, the curved portion of that graph is coming in such a way that it intersects the x-axis in exactly one spot, causing the graph to be tangent to the x-axis at that point. So that's tangent. You'll understand if we see that phrase now, we're talking about an x-intercept where my graph is bouncing. And then it goes the other way. That will happen when we have tangent situations. So when my graph is tangent to the x-axis, that means I have an even power related to that factor of x minus k. So, for example, x minus k squared, or x minus k to the 4th, or 6th, some even power right there. And when we have this tangent scenario, we talk about our graph bouncing off of our x-intercept. And that's what's happened at -1. So when we have even factors raised to an even power, my graph bounces. When we have odd factors, odd power of some factor x minus k, my graph will cross the x-axis. So it'll go through it. And these are the 2 conditions that we will have for our polynomial graphs. They'll either go through or they will bounce off of your x-intercept. So this is what we're going to look for now to interpret graphs and then hopefully be able to write the equations from them. Now there are 2 types of zeros that present a little bit of a challenge, not difficult, but a challenge. When we have imaginary zeros, when we have a situation where my graph actually physically doesn't touch the x-axis, but I still have to consider finding these answers here, because in terms of being able to factor a polynomial, I can take that factored form and expand it and write the expanded form of the polynomial. That's ultimately what we want to do when we're writing our equations. So when I have these complex conjugates, again, we're coming back to revisit those from chapter 4. If I have an imaginary zero, a plus bi, then I have to remember conjugate means the opposite sign in the middle here, so a minus bi. These 2 we call our evil twins. They are always working in tandem with one another, one of them being positive, one of them being negative. So anytime I found a zero that's imaginary, I know I have a conjugate zero of that. That will also be a part of my solution. And the same goes with the irrational conjugates. Now, the irrational conjugates are dealing with things like a plus a square root or a minus a square root. And they also have the evil twin. We have a plus b under a square root. We have a minus a b under a square root. We actually saw that example back here when we found this. You can see the conjugate of the rationals right there, plus or minus a square root number. So they always work in pairs. So if you see one, you know you're going to have the other one. So let's see how this plays out when we write our polynomials. So we're going to be writing these polynomials of least degree. So that means we're going to be thinking power-wise on our factors, smallest numbers possible. So if I know that I have a graph where I can see that something is bouncing, I'm going to talk about that as a degree of 2. And if my graph is going through the x-intercept, degree of 1. But what happens when our zeros are imaginary? How do we take this and write it into an equation? All right, so we have a leading coefficient, that's 1. And that just means I have a positive lead. So it helps me with my end behavior of the graph, if I'm graphing this thing. Okay, we have 2 given x-intercepts. We have a 0 of 2 and a 0 of negative 2 minus 5x. So immediately when we know we have an imaginary 0, go ahead and write the equal twin, because that's also going to be one of my zeros. Negative 2 plus. All right, we're going to end up with, in this case I see 3 zeros. One of them is real, 2 of them imaginary. So I'm talking about a degree of 3. So let's write the polynomial for this thing. We're going to have to give ourselves a little more room here. What do? Well, first of all, we have to remember when we're writing polynomials, if zeros are equal to this k value, we said that the factors are x minus k. And this is the part we're going to remember, or we're going to use here for writing our polynomials of least degree. We're going to write it in factored form, and then take the factored form and expand it out. All right, so if I have to do that, if I have 1k is equal to a 2, another k is equal to a negative 2 minus 5i, and then yet another is a negative 2 plus a 5i. And I have a situation where my polynomial of x is equal to, well, x minus 2 is the real part, and then here comes the imaginary parts. So let's talk about the negative 2 minus 5i. X minus that k, negative 2 minus 5a. And then the complex conjugate, evil twin, negative 2 plus 5i. And if I were to leave it in factored form, then we could stop right here. But we're not going to leave it in factored form. We're going to expand this thing out. So here's what we do with the complex guys. You'll notice that both of the imaginaries end up with a situation where I have minus a negative going right there. So really what's happening is I've got this, I've got x minus 2, and x plus a 2, and then this would be a plus 5i here. And then I have an x plus a 2 minus a 5i. And this is the part that I want us to recognize. I want us to recognize this component, the x plus 2 part. If I look at this x plus 2 quantity plus 5i, the x plus 2 is like the a part, and here's the bi part. And then over here, we have the a part minus the bi part. So really what I've got happening here is an a plus a bi times an a minus a bi. And we know that when we multiply conjugates together, we get rid of the i's. So that binomial becomes the real part a. And this is the tricky part of this. So we're going to to leave the x minus 2 alone for right now. We're going to work on this a plus bi, a minus bi form. X plus 2, there's my a. I'm squaring it. And because I'm dealing with two conjugates multiplying together, a plus bi, a minus bi, remember what that gives you is a squared minus b squared I squared. We lose the middle term. And remember that I squared is negative 1. So really this becomes I squared, or a squared, plus b squared. So that's what we're going to do here. We're going to take our a, which is an x plus 2, we're going to square it. Then we have our b, which is a 5 and a negative 5. That becomes a negative 5 squared, or negative 25 I squared. Our I squared becomes a negative 1 right there. So this becomes x plus 2 quantity squared plus 25. And that is what, so far, this whole part of the problem boils down to. And I still have out front my x minus 2 part of this polynomial. That's just right there. Then we can see that I've got x plus 2 quantity squared there that we can simplify. So I get x minus 2, and then this becomes x squared plus 4x plus 4 plus a 25. X minus 2, x squared plus 4x plus 29. Then we distribute everything, and we will finally come up with our polynomial here. So distributing the x to the x squared, the 4x, 29. Doing the same thing with my negative 2 to the x squared to the 4x to the 29. We come up with x cubed plus 4x squared plus 29x minus 2x squared minus 8x minus 58. And we simplify all this, and we come up with the answer that we were looking for originally, and our polynomial is x cubed. We always said it was a degree of 3. 4 minus 2x's is 2x squared. 29x minus 8 is 21x minus 58. So there's our polynomial that has resulted from knowing one x of 2 and the other one of negative 2 minus 5i. Okay. All right. Let's see. All right, let's try one with a an irrational conjugate. So let's try this C version here. Leading coefficient of 1, zeros of 4, and 1 plus the square root of 6. So again, this has an evil cousin 1 minus square root of 6. Every time I see that, I have 1, 2, 3 real zeros. Leading coefficient of 1. All right, this is another third degree polynomial. So we start out basics with writing it in factored form. So I have x minus 4. X minus the quantity of 1 plus the square root of 6. X minus the quantity of 1 minus the square root of 6. Just like we did last time when we had complex conjugates of imaginary numbers, we're going to consider the same thing. We're going to be taking a look at that x minus the a part of our irrational conjugates. So it looks like x minus 4, and then we get this x minus 1 part plus the square root of 6. And then there's that x minus 1 part again. This time minus the square root of 6. And we see our complex conjugates, irrational conjugates here. So this again is like saying a plus my square root of b, and this one over here is saying a minus my square root of b. And when we multiply those two together, we get a squared minus b. And so that's the pattern that's going to develop from quantity x minus 1 plus square root of 6 times quantity x minus 1 minus square root of 6. So the x minus 1s are my a's, which means this is still x minus 4, but x minus 1 squared minus 6. And then we have some more simplifying to do. X minus 4, and then x squared minus 2x plus 1 minus 6. X minus 4, x squared minus 2x minus 5. Do all of my distributive stuff here. X to the third minus 2x squared minus 5x minus 4x squared plus 8x plus 20. And we finally get our polynomial written in expanded form. Minus 6x squared plus 3x plus 20. So just remember on these writing our polynomials given zeros thing, if our zeros are complex conjugates or they are irrational conjugates, we have to be careful how we pair them up. And that happens here in these two steps. Again, it happened up here in the same location with this problem. So we wrote our factors and then we paired them up differently. So those you have to definitely be careful of. All right, let's see if we have time here to get to. This is just more of an FYI than anything. Descartes' rule assigns you to the French mathematician that recognized in this polynomial world that there was a pattern we saw between the sign changes that occurred between the terms of a polynomial and how that resulted in determining the number of positive real zeros or negative real zeros and imaginary zeros and coming up with thus the total. So we're going to real quick run through one of these. This is more just, again, as an FYI. Just helps you maybe in determining the number of real or the number of imaginary. So given some polynomial f of x in the following form up here, again, our generic form of a polynomial, the number of positive real zeros is equal to the number of sign changes in sign, of the coefficients of the polynomial f of x, or it is equal to less than, or it's less than this by an even number. I know it sounds kind of confusing, but if I had, let's say I had 5 sign changes, then I'd have that many possible positive real zeros, or 5 minus 2, there's our even number, less than 5, or 3 possible sign changes. Negatives, number of negative real zeros, same thing, is equal to the number of sign changes that we see. So now we notice it's of our f of negative x polynomial. So we're going to plug in opposite values of x. So let's see how this works out here in this problem real quick. Determine the number of possible positive, negative, and imaginary zeros. So first we'll do the real zeros, where we just use f of x. How many sign changes do we see between each of these terms? Well, 2x sixth and minus 3x to the second, that's a negative. 3x squared minus x, no difference in sign changes there, another negative. But here, between this term and this term, we see a sign change from a negative to a positive. So we have one sign change. And that equates to at least one real zero. Again, because of our rule here. The number of positive real zeros is equal to the number of sign changes. Or it's less than that by an even number. Well, I can't really subtract 2 from that and get a whole number. So we end up with just one real zero here. That's possible. What about the negative side of things? Negative real zeros. Let's look for that. This involves me taking f of negative x. So now I'm doing this. I'm getting 2 times negative x to the 6th minus 3 times negative x squared minus negative x plus 1. So we get 2x to the 6th still minus 3x squared plus x plus 1. Changing all my x values in there. How many sign changes do we see now? We see a sign change from a negative to a positive here, and then that's it. So we see one sign change for our negative, and that equals one real zero that's negative instead of positive. So we have that. Not that, just one. So you could have, let's see, let's give all of our possibilities. You could have one positive zero and no negative zeros. And then because this was a 6th degree function, you could have 5 imaginary zeros for a total of 6. Or you could have no possible real zeros and have 6 negative zeros and have no imaginaries for a possible of 6. Or you could have 1 positive, 1 negative, 4 imaginaries left over. Or what about no reals and 6 negatives? But there's some possibilities of the number of positive and negative zeros you could have and their respective imaginaries. That's Descartes' rule, real quick. FYI way of looking at positive and negative zeros. All right. And then lastly, if you have a graphing calculator, this is where you can do some approximating of your zeros with a graphing calculator. We could, in this problem here, use our P's and Q's and come up with our zeros with our rational zero theorem. Or we can go ahead and use a graphing calculator feature that allows you to input the equation, graph it, and then let the calculator do the work to approximate where your zeros are going to be. So I'm going to just show on this real quick how we can do that using our Casio. First thing we'd have to do, though, is we'd have to, now if you don't have this is the TI Inspire, but TI 84, 83, you can still do the same thing graphing-wise, but I'm just going to show you what this would look like. First of all, we would have to put in our equation. And our equation, going back here, 4x to the 5th plus 12x to the 4th minus x minus 3. All right. So 4x to the 5th, and then plus, I believe, was it plus 12x to the 4th minus x minus 3. Okay. Plus 12x to the 4th minus x minus 3. All right, we got it in there, and then we can go ahead and hit enter. And there's our graph. And let's move this out of the way a little bit. So we can kind of see where crossing the x-intercepts. 2 of them don't appear to be. It's hard for me to interpret where the 2 that are next to the y-axis are actually crossing at. So now we're going to use the approximating tool of our calculator. And in this calculator, you get to that through the menu option. And we're going to analyze our graph, and we're going to find zeros. And the first thing it does is ask me to identify a lower bound. What that means is the lower bound is the left-hand side of where you think your x-intercept is. So I'm going to click right on the left-hand side of that blue line. And then it's asking me for my upper bounds. I'm going to click on the right-hand side of it. And then it'll approximate it at this time negative 0.707 for that particular zero. And then I'm going to do that again, analyze graph, find the zero. And again, lower bound on the left-hand side of where I think this zero is located, right about there. The upper bound on the right-hand side, and it finds that guy at positive 0.707. Now we might want to check the one on the left. Make sure.
Student Jonathan Dyson.
Analyze graph.
Sarah Barker.
Go to the left, go to the right.
Mary Bell.
There's my zero
Please report to the
negative 3.
attendance
So
office.
the graphing function tool,
Jonathan Dyson.
very helpful
Mary
for
Bell.
approximating your
Please
zeros
report
if
to
you
the
have it.
attendance
Use
office.
it. There we go. Hope that was helpful.